cool. Perfect. Right when I was singing. A lot actually happens on stage when the mic's off. Like Steve and I were just arguing about who's getting older faster. But luckily, he's doing really productive stuff with his aging energy, such as working on the IOPipe library. So he's here to talk to you about that, which is much more interesting than my singing. So if you could be quiet now, everyone. Seems like that unprecedented power only works when we're talking about things versus Walter and Andre.
That's right.
What's that? Do it in German? That's kind of my confession. I've been in Germany for a really long time that I learned to be fluent in German and then forgot it completely. Okay. So, nice, that worked. Take it away, Steve.
All right. Hello, everyone. I'm going to talk about my IOPipe library that I kind of released it last year just before the DConference in a very preliminary state. It's still kind of preliminary. It's not ready for prime time, but it has come a long way. It's a library to use direct buffer access to enable more optimized usage of buffer data. So the first thing we need to realize is that I/O is slow. Anytime you're moving data from a device into memory, it's slow. It's got to come from a physical disk or wherever it is, go through buses, routers. So there's a tremendous lag. So anytime you want to read some data, you don't want to read just 1 byte from a disk. You want to get a whole bunch of data. Now, if you're only interested in 1 byte, then you don't want to throw away all the data that you read, so you got to put it in a buffer somewhere. So that's why we have buffering. It's necessary for performance, as I said, but when it's used only as an optimization, then it's wasted opportunity. Because when you have a buffer and you can look through the buffer for whatever you're looking for, backwards and forwards, there's a lot of potential there. And buffer access is very liberating. Every copy counts. Every time you copy memory from one place to another, the CPU could potentially be wasting cycles. And performance is trumped by API correctness. So if your API is expecting to give you a byte at a time, then it just hides the buffer access underneath and doesn't give it to you. But that's not an inherent problem. So let's look at a use case, buffer access. Byline, simple function here. We read data until a line ending is found. We provide the line data in an array or range for processing and save the rest of it that had been read for later. And then we use the buffer. The next time we reuse the buffer for the next line. So let's look at the FileStar API. Everyone knows what FileStar is, right? It's the C buffering stream. Buffers data for performance reasons, gives you 1 character at a time. I know it comes out as an integer, but it's still 1 character. And you have no direct access to the buffer that's hidden underneath it. So let's look at what it would look like if you were to implement the piece of Byline that actually gets the next line from one of these FileStars. So we start out with a line. We're going to store it forever so we can keep reusing it. We reset it so that it's, we're not wasting that memory and allocating new memory. While we get a character and it's not -1, which means end of file, we're going to append the character to the line. If that character happens to be the new line, then we break out of our loop and return that line. Next time we come back in, we'll do the same thing. How many of you guys use DMD on Windows 64? This is your implementation of Byline, by the way. This is all that Windows 64 gives you because it does not give you any direct buffer access. So it's slightly better. It doesn't do the array appending, and it does lock the stream and stuff like that. But essentially, this is what it is. Now, Phobos uses FileStar, so stdio file uses some tricks to get around those limitations. The code for readline implementation, which is basically the thing we just looked at, is 357 lines of code. That basically includes three or four different implementations of Byline, just so that we can use the different tricks, like this function called getDelim, which ironically, it does have direct access to the buffer because it's written in C and it understands the C library, what the actual structure is. If you're on Windows 32-bit with DMC, then we know the author of that library, so we can look inside that struct and know exactly what the buffer looks like, and use that a little bit better. Unicode delimiters are not supported, not completely supported. If you actually on Windows, if you ask the stream to become a wide stream, it just basically ignores your request. So it still stays a character stream. And there's other limitations. We have every FileStar is implicitly expected to be shared between threads. So anytime you do anything with a FileStar, you have to lock it. Phobos kind of locks it around its operation, so it doesn't. It gets a little bit better performance. But even if you're just having that one FileStar inside one thread, just to read lines out of a file, you still have to pay for that cost. So IOPipe takes a different approach. We provide direct buffer access, so there's less copies. So if I read data out of a file, it goes into a buffer, and you have direct access to that buffer. That's where your line is returned from. It's all decode, so much better API, all inlineable. The compiler can see everything. There's no opaque function calls. getDelim is an opaque function call. And there's some. And it's also the byline code that we use in IOPipe is actually only 170 lines of code, and there's only one implementation. We don't do multiple implementations for different tricks, for basically based on the underlying functions that we have to call. There is some optimization for other things, but it's mostly based on the types that you're trying to read. We don't rely on opaque shortcuts like getDelim. And I have full Unicode support, so I support Byline can work on UTF-8, UTF-16, and 32, any kind of delimiter there. And it's 2 times faster than Phobos Byline. And it's also 1.5 times faster than getLine directly. So it offers a significant performance improvement. So the IOPipe API, 3 simple primitives, kind of similar to ranges. Window gets you the current accessible buffer as a random access range. So all the data that's in the buffer right now, you get complete access to it. There's no notion of a file pointer. You'd have to kind of store that separately if you want to do that. Extend says, I have this buffer, but it's not enough. Let's say I don't see a new line character in my buffer. I need more data before I can return. So it just says, give me more data. You can pass in the amount of data that you want, or you can just say 0 and it'll extend some optimized amount based on the IOPipe's implementation. And the last piece is release. So this is saying, I'm done with this part of the buffer, just get rid of it, and I'm only going to focus on this. This allows the buffer manager to reclaim that data. It's like freeing that data, and it can reuse it for later. And there's one small difference between IOPipe and Phobos, and that is because there's a lot of focus on text processing. I use character buffers or character arrays as my buffer, and Phobos does not treat that as a random access range, but IOPipe does consider a character array to be a random access range, because all I'm basically doing is reading and writing from that. I don't want to decode it. So let's look at the extend function for Byline and IOPipe. At the top, we store a reference to the window. I realize when you don't do this, it hurts performance quite a bit. Same thing with this is basically the implementation if your delimiter is one code unit out of the stream. So new line is a good case for that. So if you're looking for a multiple code unit delimiter, then it's a different branch. We're actually not going to look at that today. But basically, if it's an array, then we know we can use pointers. So we'll use pointers, they're faster. And if the array's code unit size is 1, which means it's a character, then we can use memcur. Memcur is very, very fast. This is actually the magic trick that allows me to be faster than Phobos and C. It's because Phobos and C both use that under the hood as well, but because of the extra things that I do, direct buffer access and the ability to inline, that's why I'm able to get faster than them. Look for the delimiter. If I found it, then I'm done. Otherwise, it's going to loop around. And we'll see if it's not the size of a character, then we still can use pointers. It's faster than iterating over the range just by index. Basically the same thing. And then, if it's just some other type of random access range that we can't use those tricks, we just look through one character at a time, or one element at a time until we find it. So it basically gracefully degrades into the highest, it tries the highest performance thing, but it'll gracefully degrade into the thing that works the best.
Steve?
Yeah.
We have a comment from the chat from Gallier2.
Yep.
You can have buffer access on FileStar and C. You have to set your buffer with setVbuff.
That is true, but the problem is that FileStar expects that buffer to be a malloc buffer, I believe. So I don't think that you can't just use any buffer. Plus, what we're doing is actually extending the buffer if we need more data. It's not something that you can do with FileStar, I believe, unless you kept resetting that. But I don't think you're supposed. Once you set the buffer, you're not supposed to do it again. I'm pretty sure about that.
Cool. Thanks.
All right. So one other thing to recognize here is that IOPipe Byline is an IOPipe. It's not a range. What it is a delimiting IOPipe. So when you extend more data, it extends one line. And then we wrap that with a primitive I call as input range, which basically says the front is the window. When you do pop front, I release all the data out of that and extend the next one. So just naturally, like by chunk or by line, naturally maps to that pretty easily. And I also provide a byline range special case for optional line endings because I'm not removing anything from the data stream, but I can slice off that new line ending if you want when you're actually using it as a range. But you can do some nifty things with this because you can imagine if I could just get one line at a time and release one line at a time, you could keep multiple lines in the buffer itself. So if you were, let's say, printing out an error message and you want to give 2 lines of context around that, you could just keep the last 5 lines in your buffer and be able to print those out and still access those.
We also have a bit of encouragement from the chat. Dejan is saying, I'm already in love with IOPipe.
Great. I hope people will like using this. All arrays are IOPipes. The complete implementation is right here. Obviously, you can't extend an array. There's no more data to get. And the entire array is the buffer. And release just slices off the front. Very simple. But what this does is all the functions that I provide that deal with IOPipes work on strings, work on array literals, anything you want to work on, it's there, it's available. And as a nice feature of that, testing IOPipes is very, very easy. You just pass a string into it, and it doesn't matter that you don't really have to. It's good to test it against actual files and actual streams and stuff, but the correctness is going to be tested just by using a string, and you can, build whatever crazy cases you want right in line for your unit tests. The other thing is that I could extend this to just any general random access range. but for my purposes, because Phobos does not consider character array a random access range, I kind of did it this way because it works for me. IOPipes use chaining, so if you have, I'll just show 3 examples of what we do here. If we want to open a file, that openDev is from a very basic stream type that I have in my library. It's not something that it's the focus of the library, it's just something I wrote like 4 or 5 years ago. But any kind of device reading mechanisms, such as stdio file, as long as it supports a read function which accepts an array and returns the number of bytes or the number of elements read in that array, it'll work. So openDev opens a file, and then we buffer it, convert it to UTF-8. I know it says decode text UTF-8, but actually file returns UBytes for a sane implementation. So we need to convert it to UTF-8, which is a character buffer. And then we hook byline range, and that works. If you have a compressed file that has lines in it, I provide a unzip and zip IOPipe. We can just pipe it together, and it works exactly the same. Unzip decompresses to a UByte buffer, and you just run it that way. Same thing with an array literal or a string literal. You can just run it that way, and it works great. So output is a little bit harder, because for an output, when you all my types in IOPipe are pulled. So you pull them by looking at the window and extending and releasing. However, output needs to be pushed. First, you need to write the buffer, and then you need to push it down the pipeline to something else. And IOPipe, as I said, uses strictly pull mechanism. I didn't want to implement different methods or different pipes for byte swapping. If you're pull byte swapping versus push byte swapping, I didn't want to do that. So I said, how can I do this where I'm still just pulling? And once you build this pipeline where you have your buffer, and then let's say you're writing to a file, I want to convert it or whatever, at the end, all you have access to is the end of the pipeline. Just like a range, you don't have access to the converters all up front. They're just kind of hidden underneath, and that's kind of a good thing. But we need to access to the front, which is where the buffer is. So the solution I came up with was valves. Now, I've tried to explain valves several times, and each time I think I failed miserably. It's kind of a weird thing where it just gives you access to an upstream pipe. And the way I had it set up, I think last year when I did my talk at the D Boston meetup, it generated some confusion and suggestions on the forums of better ways to do things. And this I wanted to point out was a message from somebody that said, why don't you do it this way, where you have an array literal or a delegate that then runs those things. And I said, I could do that, but I don't like it. And after about, 3 or 4 months, I've come around to actually like this. So thank you, John Colvin. This is now the way that you do pushing an IOPipe. It works so much better than the other way, which I'm going to show you in a second. But the only thing I didn't like about it was this whole arrow A nonsense, but that's just because we needed a template delegate literal. All I'm doing is I'm putting some mechanisms on the front, then running those things, and then putting some mechanisms on the back. Very simple. And this is code from a converter that I wrote. It's in the examples directory in IOPipe that takes any form of UTF and pipes it out to standard out to a different form that you specify. So if you think about input is an IOPipe that's either character, W character, or D character buffer. I call ensure decodable on the end of it, just to make sure that I don't have a slice of a code point. That's another wrapper that I provide. And then I say, as an input range, And then for each of those window buffers, I'm putting it to this output chain. Now the output chain is a buffered W character, let's say, and I'm going to push it to this little pipeline that first encodes it as UTF-16 little endian, which would be, on a x86 would just be straight copy, but on another machine would actually byte swap all the W characters for you, and then outputs it to the result file. Then I wrap that whole thing into a text output range, so it just works with any, just like you would use an output range in Phobos. And because that push just gives you access to the buffer, because it's a valve, it looks to you like you're just writing to a buffer and releasing it out, and eventually at some point it's going to fill up that buffer. You're going to say, I need more space so I can write to it, and at that point it's going to write that buffer out and then reuse the buffer for your next, give you more space to write in. So, as I said, a valve is a control point along the range, or along the chain, allowing direct access. All IOPipes are required to implement a valve, access to the next valve if there is one. So, I have a mix-in that basically says implement valve if your input IOPipe has a member named valve, then it just adds an extra accessor for that valve. Otherwise, if you're actually implementing a valve, you would do it differently. But this is, in a push IOPipe is really a pull IOPipe wrapped into what I call a holding valve. Basically, when you release data out of that buffer, it goes into a holding area until it's ready to write it, and then it all gets run through the rest of the output chain. This is what it used to look like before John had his great idea. And these different things, first we start the loop. Those are the two IOPipes that are added that do the output. Then we close the loop, that just gives the access to the range, and then this auto-flushed is something I added recently, which flushes the whole thing on destruction. You kind of need that because if you run your whole processing thing and you forget to call flush, there may be some data in that holding area that doesn't get pushed out. So auto-flush adds a destructor which does that, and it also makes it ref counted so that we don't flush multiple times as you're passing. You pass these around as with value. You construct with value types, so you're not actually passing references around. But so we have to ref count that whole thing and then turn it into an output range. So is there any questions on valves or? All right, so we'll move on. So let's look at a use case of parsing JSON, which is something I added a couple weeks ago. This is an implementation of JSON tokenizing using an IOPipe as a source. So we've taken the IOPipe and a position that we are in the buffer. First thing we do, check for white space, extending until we either get end of file or we find a white space. Pretty simple. JSON is very simple to parse. Every token starts with exactly one ASCII character, so it's very easy to look for that ASCII character. This is probably familiar stuff for some of you. I know there's a lot of talks this year about JSON parsing, so that was just the thing that finds the next token. This is the function that gets the token. Validate token, it's just a simple function that says, give me, in the stream I have this, I'm expecting this exact string, like true, TRUE, find that, and make sure it matches. And finally, while we get our JSON tokens, for the simple ones, they're just the length 1. For end of file and error, they're done. Otherwise, true, false, null, straightforward, just validate that they're there. Strings, I have a function that basically parses the entire string, make sure that the data is in the correct format according to the JSON grammar. And there's a replace escapes Boolean that will basically, in place, because you have access to the buffer, if you have any escapes, they'll rewrite those escapes as the actual characters that they are. And it turns out that this is always possible. So at the end, you can slice basically a piece out of the buffer, and it's an actual string, or W string or D string, whatever it is. Similar thing with parse number, except at that point we're not actually creating a number out of it. We're just figuring out, does it follow the grammar, and how big is it as a string. And this is it. There's no memory allocation here, just using the buffer completely. And then I have a JSON tokenizer, which is just slightly, just a layer on top of that verifies that like you can't have 2 commas in a row or things like that, and it keeps track of the position in the buffer for you. So the tokenizer and all these related functions are about 480 lines of code, and half of that is mostly for parsing making sure the strings and the numbers are in the right JSON format. So it's pretty compact. Sorry. And this is now a DOM parser. So we're going to parse the JSON similar to, it's a recursive descent parser. Basically, while I get a next item, I'm going to build an object or build an array. When underneath, there's things that parse out the strings and the values according to what they are. I didn't write that code because it's pretty straightforward. This will also, if you pass duplicate equals false, will never release any data from the buffer, and it'll slice everything right out of that, so there's no copying from the buffer. The only thing is it does right now, it doesn't take an allocator to allocate actual JSON elements. It's going to append those to an array or put them into an object, associative array for objects. Very similar to how std.json works. In fact, I pretty much stole that JSON value type from there. This JSON parser is 249 lines of code, including comments and unit tests, so also pretty small. And the other day, Daniel Murphy was asking, how does it actually perform? I said, I don't really know. I've never tried it to test the performance. So he gave me a challenge of just taking JSON stream and reformatting it to be basically pretty printed without any allocation. I said, yeah, I can do that. So I think a couple days ago, I think I wrote it in like 10 minutes. And we sat and maybe optimized it for about 40 minutes. I don't know, something like that. And I will show you how fast it is, basically. If I can get this over there. So this is the pretty printer. It's you can't really see it, but there's basically 90 lines in the file. We have a parser that we create, tokenizing with false, saying we don't want you to replace anything because we're just going to output it. It's not like we need to look at the strings. The outputter is also an IOPipe, and we keep track of indentation. This is the thing that actually outputs, the indent and the new line. So first we make sure there's enough elements in the IOPipe that we can just slice it in. We write the new line, we write the spacing based on this, and then we release. The release is the thing that puts it into the holding area so that it can actually be written when it's filled up. Same thing with the string. This is even more straightforward. And that's it. This is all the mechanical things that we would need to actually do the input and output. Now we just basically, this code is pretty straightforward. Object start, we put a bracket, we increase the indent, that kind of thing. And it's not too bad. So, and you can see that I didn't do any specialized, table lookups or SSE or anything like that. It's just straight code. And the performance is not too bad. If I build this, okay. So JSON. Apologize, I have this dual screen, so I can't see what I'm doing. So if you look at the, this file, it's basically unformatted and then magically becomes formatted. Yay. But the real test is, how does it do it if you were doing a very large file? So if we look at this file, it's basically, I went to a website and generated some random JSON file, and then I repeated it about 10,000 times. So the file is it's 362 megabytes. This is the only way we could get some kind of reasonable performance metrics out of it. I don't know if you guys are familiar with PV. I think I have this in my command line here. So PV basically tells you how much data is coming through me, and it's a pass-through, so I'm just passing it out to null, dev null. And so we get decent performance. I'll run it a couple times to make sure there's no issues with caching. So we get about 100 megabytes per second, not too bad. But I think we can do better. So if we go back in, I have already here, instead of using my file stream, let's use a memory map file from Phobos. Basically the same thing. Here we're kind of cheating and casting it to immutable. I don't want to write to that file, I just want to read from it. But create a new memory map file, cast it to immutable char, and then it can go right into, it's an array, so it can go right into the tokenizer. Same exact thing. Let me make sure that you can see this. So we get about 50 more megabytes per second by doing that. But I'm still using DMD, so let's see what happens when we use LDC. And there you go, it's about 215 megabytes per second. So just with some simple speed ups, we can achieve that. I also had a thought, well, I don't even know what this means. What does it mean to parse 215 megabytes per second in JSON data? So I figured there's other people who've done this, and they probably did it in C or C++. As it turns out, there's a website that has a list of about 40 C or C++ JSON parsing libraries and lists them in order of their performance. And I just picked the fastest one. And they happen to have the exact same test, prettify this function. So you can see here that basically it's called rapid JSON. I don't know if anyone's heard of that. We have a file read stream. We're going to open the file. We create a writer for it. These are all their specialized types to deal with JSON parsing. And I feel it's maybe a little bit less. Like if I wrapped my pretty printing function into a library, it probably would look a little bit better than it did. But even so, this is obviously C++. It doesn't look that great. So if we build this, yeah, that should work. And then we run it, same way we were running our thing. What do we get? It's about 150 megabytes per second. That's without using a memory mapped file. But I looked kind of in the code of where they're doing their JSON parsing, and they're using things like unlikely and likely and lookup tables and SSE2 and all these things. So I'm sure we could get IOPipe's JSON parser to be faster than this, but got pretty decent performance without that. So I also said, well, if I want to compare apples to apples, we should use memmap. So similar to what I do, they have a stream to read JSON data right out of memory. Mmap file is just memory, so not a big deal. Try it again. And surprisingly, this surprised me a lot, it's still only 150 megabytes per second. So with LDC and memory map files, we can actually beat significantly the fastest JSON parser available on the internet after searching for about 5 minutes. So. So let's see. All right, so there's definitely some potential for doing some parsing with IOPipe. It makes things very easy to write. I'm going to test that. It was very, very simple to write the JSON parser. Of course, JSON parser is pretty simple to write to begin with. But so what are we doing for the future? So for the future, I would like to do an XML parser. I know that there is an XML parser in the works for Phobos. That's I don't know what it uses for buffering, but obviously it would have to use IOPipe would have to be in Phobos for that. But I'd still like to try and do some XML parsing, see how it works. Another library that I use quite a bit is the MySQL native driver. I think this would be a good fit for there because basically you're reading data in and you're parsing out packets, and it would be a natural fit for that. Imagine you have a whole row in memory and you just slice information out of it. Vibe.d, I also use Vibe.d quite a bit, and making IOPipe hook onto the, onto the Vibe.d streams would basically give us a free asynchronous mechanism to do buffering there. And potentially, maybe, I don't know. It could get into Phobos, but that's not something I'm looking at this second. I know a few years ago I was looking to actually replace the streams in Phobos. I know with standard stream going away, but I'm not sure that that's going to happen. We'll see.
Steve, there's a comment from the chat from
Yes.
Neo saying, should compile with CLang rather than G++ would be better comparison to LDC, I think.
I think that's true, except I'm on a Mac, so and my Mac is Xcode, so it is actually, I believe it's LLVM. Is that correct? Yeah, so I think it is actually LLVM. And that's it. I guess I'm a little bit early. But any questions?
It's not just the content of your talk that's fast.
Hello, Steve.
Hi.
First of all, thank you very much for all your help in merging the runtime PRs.
Yeah.
Review is very appreciated. What I was going to say is that you were surprised how the mmapped C++ version 1 was not significantly faster than a read one. I was surprised how the D solution with the mmap, given that you're not doing any random access touching the file, I was surprised how it is significantly faster than the read one, unless the pages are already cached in memory or something like that. I didn't expect like almost the double of the, or 50% of
Right.
the heads
Yeah.
up. Is there a significant overhead in the library?
It should be very, very small. I mean, remember, all these things are hooked together and they can be inlined, and the optimizer can go nuts on the whole thing. So it should compile down to something very, very small. And I think that might be an explanation of why it's better. Martin?
Maybe I might say something to that. I have an assumption that simply the window buffer is very small, so you do a lot of I/O calls to the kernel actually, and that's just maybe the overhead that's accounted for.
It could be.
So because usually for single through read like memmap and stream reads and stuff don't make much difference.
I don't think the JSON parsing part will be inlined by DMD because they use a switch and the inliner gives up on that.
Okay.
So probably you could have even more performance if you change it into an if-else chain.
I think it might be better to maybe fix DMD optimizer then. Yes.
Regarding the mmap1, I'm not 100% sure, but as a comment, I'm using map populate, because if you don't use it, it's essentially not preloading the file into memory. It's just doing it lazily when you need it.
I literally wrote it in like 10 minutes, so whatever the default is, I think.
The default, I don't know if what's on a Mac, but on a Linux, if you don't use map populate, it won't.
Yeah, this is on a Mac, so it might be different, but where is it?
Steve, just... Oh, sorry.
Yeah, it's, all I'm doing is using whatever Phobos does. So
Okay. Yeah.
Yeah, my assumption was that for your second run, your file was already cached in memory, so there were no page faults. There were no, getting the file from the file system into the RAM. So if you could run the read one again, maybe they are completely different. Or what Martin said about the small buffer size, but this is
there's
not important for this talk.
There's so many moving parts here that I'm sure there's some things that that cause it to go faster, but still, I mean, it worked. So
Yeah.
Yes.
So this is already impressive enough to me, and I work with big data, so I really want to use it.
Good.
So it is a usage question. So suppose like user can describe the data structure as a struct. Then can we use, or we need be able to use the struct to pass the files and return a lazy range?
Yes.
Yeah.
Yeah, there should be no problem there.
Yeah. Thank you.
In fact, that's what I plan to do with the MySQL, native MySQL driver, is parse, instead of, right now, native MySQL, and I know that Nick changed the interface and I haven't gotten a chance to use it, but right now it basically sticks everything into variants, and then you take those variants and put them, if you're putting them into struct, so you have this weird like double move of things, but I'd like to just parse that exact data right from the row data right into my struct, so it skips that whole step.
So you've got this kind of alternative way of iterating over things, including buffering. As it's not ranges; it's a different thing.
Correct.
And it looks great. Have you considered opportunities for using it for more just general purpose data processing internal to applications as opposed to focusing on I/O?
It absolutely could be. I mean, the source is something that provides an extendable random access range. So that could be anything. It could actually be a random access range of JSON objects. You know, so you definitely could build layers on top of layers that do those kinds of things.
Yes. And a question for me. This looks like it's essentially completely synchronous, which is totally fine. But my question would be, have you considered making it possible to use IOPipe as a processor behind an asynchronous library that essentially fetches in chunks?
That was my hope for using vibd asynchronous reading. So basically, vibd provides, and Sank is here, so he might be able to elaborate on that. But basically, I think vibd already has some mechanism to put a fiber to sleep if there's no data available, and wake it back up when the data is available. So you basically get asynchronous processing, but written in a synchronous way. So that was my hope to do that. I'm sure there's ways that you could do it asynchronously, but it would be something outside of IOPipe. It would have to say, when you get this data, run this IOPipe on the side. It still needs to kind of be synchronous. So I don't provide any mechanisms to go back in.
My hope would have been that essentially IOPipe, you could make a front end that gets its I/O in chunks asynchronously, and then forwards these chunks to IOPipe, and IOPipe then does the rest.
Yep. I mean, you could do it similarly, maybe to the way the holding loop works, where you push it, but it just puts it in the right spot, and then calls something, and then pull it through the whole pipeline. So you could do something similar to that.
Okay. Thank you.
Yep.
We also have some comments from the chat. A lot of praise for the talk, so kudos to you, Steve. And also Dejan says, I humbly believe that replacing the deprecated streams with something based on IOPipe is the way forward. QZNC says, a more thorough evaluation would be a great blog article, so if you feel like writing. Mike also agrees with that. Looks like you have some writing to do on your travels home.
There you go.
As well, there's some more comments. I know for sure that I will use IOPipe for our parsers. We process terabytes of data from exchanges on a daily basis. At the moment, it is all Python 3, but I can see that with IOPipe, it can be up to 20 times faster. Is that you in the chat, Mike, saying about the blog article, or is that another Michael? Yeah, there you go.
Great.
Any responses to the...
Thank you all. I mean, that's great praise. Thank you.
So if there aren't more questions, we'll let Steve get off stage and win ourselves a couple of extra minutes in time. So we'll take about a 10-minute break, and we'll try to start a little bit early to save more breathing room for the lightning talks later. So see you back shortly.